So, hello everyone. It's such an honor to be here. I'm a graduate student from University of Wisconsin, with my bachelor degree from Peking University. Today, I would like to present our latest results of the measurement of the Higgs boson coupling strength in the Atlas experiment. So, since the Higgs discovery in July 2012, we are now in the precision measurement era. So, in June 2014, we have two-channel combination of mass measurement from the Higgs to diphoton and to 2Z channel, which has the highest mass resolution. And then in March 2015, we have multi-channel combination of spin parity measurements, which suggests that the Higgs particle is consistent with the hypothesis of a spin-zero scalar particle. And also in the same month, we have multi-channel combination of coupling measurements of all the decay channels we have at the moment. So before measuring the coupling of Higgs boson, we need a precise mass measurement. We have combined these two channels. One is the ZZ channel and one is the diphoton channel, and obtain the combined Higgs mass at 125.36 GeV, which is also the value used in the current Atlas coupling combination. So in these two analyses, we have an updated energy calibration, which results in a better mass resolution. And also the two individual analyses are designed specifically dedicated to the mass measurement. So the most straightforward model is to measure the common signal strength, defined as a ratio of measured signal event yields to standard model expectation, which accounts for all the production modes and the decay channels. So this could be the most precise measurement because we have all the data to constrain only one free parameter. And however, there's no straightforward physics model interpretation for this model, especially for the signal strength larger than 1. The combined results includes 7 decay channels and has a value of 1.18. And the consistency test with respect to the standard model expectation, which is the scenario when mu equals 1, is 18%. One note here is that this number is the larger the number, the more standard model like the actual results. So one step further, we could decouple the signal strengths of different production modes and decay modes, and also take the ratios of the cross-sections and branch ratios, such that this could be measured in a model. Could measured in a model-independent way. This particular model is extremely useful to determine the evidence of different production modes, especially for the three smaller production modes. As you can see from here, the cross-section is much smaller than the dominant one, gluon fusion. So the evidence of the production modes is 4.3 sigma for the vector boson fusion, and 2.6 sigma for the associated production with a vector boson, that's with WOZ, and also the significance is 2.4 sigma for the TTH process, which is the associated production with a pair of top quarks. So now we're heading to the coupling measurement. So we know that Higgs coupling to other particles is proportional to the Fermion mass or the boson mass squared. In our model, we implement the coupling model using a leading order tree-level motivated framework with the 3 assumptions listed below. One is that the signal in different channels originated from only one single resonance, and the second is the narrow width assumption, which justifies the zero width approximation. And also we assume that Lagrangian structure of this particle is the same as standard model Higgs, which means it's a spin-zero scalar particle, which has been confirmed by the previous spin parity combined measurement. The coupling strength the coupling strength has been parameterized using the scale factor kappa I here, with respect to the standard model cross-section or partial decay width. So let's go to the first groups of models, which is the simplest one, to probe the coupling to Fermion and to bosons, since these two are essentially different. the loop processes, which is the coupling to photon or to gluon, expressed in terms of tree-level coupling factors, and assuming no beyond standard model contribution in this model. There's one thing interesting here is, as you can see, the coupling factors appears in squared, which means you can't decide whether it's positive or negative. However, in the parameterization of the loop processes, for example here, you can see there's a large interference term between the W and T loop as in this model. So in that case, we could actually reduce the ambiguity of the relative sign of these two different coupling factors, and we found that the negative branch has been disfavored at about 4 sigma. And also, in this model, we assume no beyond standard model contribution to the total width, such that the total decay width has been parameterized as this. Okay, so as you might find in this formula, that this total width constraint actually strongly constrain the Fermion coupling. So we could relax this assumption by using the coupling ratio here, absorb the kappa h into one parameter, such that it could be such that there's no constraint on this one. And in both cases, we found the observed data is quite consistent with the standard model expectation, and the compatibility test suggests that that this consistency with standard model prediction is 41%. So, furthermore, we could decouple the couplings in the Fermion coupling sector. First test is to test the up-down type Fermion symmetry, which could be used to test extension of standard model. And the compatibility suggests that the consistency is at 51%, and the evidence of Higgs coupling to down-type down-type Fermion is 4.5 sigma. And similarly, we could test the symmetry of quark-lepton coupling. And again, we have a compatibility at 53%, and evidence of Higgs coupling to leptons, majorly to mu and to tau is at 4.4 sigma. Next one, this is a model to probe the beyond standard model contribution to the total decay width. So we add one parameter, which is a branch ratio of invisible or undetectable processes into the previous kappa V, kappa F model, such that we allow a variation in standard model coupling and the total decay width with two additional constraints. Either we will require the kappa V to be smaller than 1, or by including the off-shell measurement, we assume that the coupling strength of the off-shell Higgs is the same as in the on-shell measurement. And again, we assume there's no BSM contribution to the loop-induced processes in these models. So since the constraint from the off-shell is actually weaker, we find the 95% confidence level constraint on this branch ratio invisible is at 52% for this off-shell constraint, but at 13% for this kappa V smaller than 1 constraint. So last but not least, the most generic model that we lose almost all the assumptions, and so there's no assumptions on the loop processes or on the total decay width. This one could be particularly interesting. Well, for example, we could use this to probe the custodial symmetry, which suggests that W and Z boson have related coupling to Higgs boson. So I find here that the result is quite consistent with the standard model. And one thing interesting is that we can actually probe the relative sign of coupling to W and Z, because we have included these very small production modes at TH or GGZH in our latest analysis, and we find that the negative solution has been disfavored at about 0.5 sigma. So it's a conclusion. So Higgs physics has apparently entered the precision measurement era. The Atlas combined mass measurement yields 125.36 GeV. The evidence of production modes yields 4.3 sigma for VBF, 2.6 for VH, and 2.4 for TTH. And the coupling measurements, however, are consistent with the standard model expectation at a level of 2 sigma or better for all the coupling models considered. the combined coupling measurement of both ATLAS and CMS experiment is ongoing, and we are hoping that more precise measurement will be achieved with data from the upcoming round 2. Thank you. Yes.
So how much smaller is the coupling to fermions compared to the coupling to vector bosons?
I'm sorry, can you say that?
I mean, you expect the coupling to fermions to be smaller because that would be like Yukawa coupling, right?
Well, the thing is that we are actually measuring the coupling ratio here. That's the observed coupling over the standard model expectation. So from this model, you can see that, well, it's actually quite consistent with the coupling in the standard model prediction. We are not saying if it's smaller than the vector boson or not. Fortunately, no.
Everything is consistent with standard model.
Quite consistent, actually. But there's a separate beyond standard model coupling measurement ongoing. So, thank you. Hey.
More than one Higgs.
I see. Well, as you can see here, in the whole measurement, we assume there's only one Higgs, so we're not considering that assumption yet.
Thank you.
Thank you.